come to class, right? All right, so last time we were talking about chemical quantities. I put molecular quantities up there. I think I'm going to say chemical quantities, right? And we talked about using them for unit conversion type problems. And so we had some chemical quantities that we used for the unit conversions, and we have up to 3 right now. So what were one of them? Can anyone give me one of the chemical quantities you use for unit conversions? For example, how do we go from moles to mass or mass to moles? Molar mass, right? So think about it. So you say it really fast, it gives you the name, right? Moles to mass, molar mass, right? So we have the molar mass, and that goes between grams and moles. And so the way we think of this conversion is when we're going between moles of a substance, that's like the actual number ratios of everything, right? So we can't convert directly from a mass of one substance to a mass of an element within that compound, for example, because elements have different masses, right? So there's not a one-to-one relationship between masses of molecules and masses of the elements. What we do is we convert it into moles first, and moles gives us the ratios, right? The number amounts, which is why if we have a molecule like benzene, C6H6, we'd say for every 1 molecule of benzene, we have how many carbon atoms? 6, right? And for every 1 mole of benzene molecules, we have how many moles of carbon atoms? 6 moles of carbon atoms, right? So we convert into moles because it actually gives us the ratio between the individual elements in this molecule and the number of molecules that we have, right? And the molar mass allows us to go from the mass because that's something we can actually measure. We can't directly measure the moles of a substance, right? We can't go in the lab. We don't have anything that directly measures them. So we measure the mass indirectly and then convert that into moles. What was another thing that we can use to convert? We have Avogadro's number. And what 2 things are we going between when we use Avogadro's number usually? Number of things, right? Number of things, and things in this case can be atoms, molecules, ions, proteins, cells, whatever we want, right? Number of things and what? Moles, right? So this goes between number of things and moles. Generally, we don't get the number of things, right? We have no way to measure the number of atoms in this table, for example, because they're so small, we have no direct way of measuring that, right? So usually we're going from moles to number of things, after we measure the mass, right? So we go from mass to moles to number of things. And Avogadro's number was N sub A, 6.022 times 10 to the 23 number of things per mole, right? Those are the dimensions of that number. And what was the thing that we introduced last time that we started talking about? It was the molar ratio, right? The molar ratio. And where do we get the molar ratio from? We actually already talked about it for a brief second, just a little bit ago.
Like how many of one atom is in the entire thing?
Yeah, we get it from the chemical formula, right? That's where we get this from. We get this from the chemical formula, right? And from the subscripts specifically. And we'll also get it from chemical equations as well. And that's what we'll get into today. Right? And it says, for example, if we have benzene, right, we have this molecule here, and we have 1 mole of benzene. How many moles of carbon is that going to equal? 6 moles of carbon. Right? And where do we get the 6 from? Well, that's because the subscript right here is 6. So for every 1 mole of molecules of this, because for every 1 molecule we have 6 carbon atoms, for every 6.022 times 10 to the 23 molecules, that means we just have 6 times that many carbons, right? And that, what is 6.022 times 10 to the 23? That's just a mole, right? That's just our counting device for making dealing with very large numbers a lot simpler. And if we were to make this into a very specific ratio, we get 2 conversion factors from this. And what are our 2 conversion factors?
6 moles of carbon.
Yep.
Over
6 mole carbon,
1 mole.
1 mole C6H6. And what's our other one? The inverse of this, right? 1 mole C6H6, 6 mole C. Right, which conversion factor we use always just depends on which direction we're going, right? If we want to end with units of moles of C6H6, which one would we use? The right or the left? We would use the right, because this has moles of what we're interested in the numerator. If we want to go the other direction, to moles of carbon, we then use which one? We use the left, right? Because we're going to moles of carbon, and that's in the numerator. Right, so we can think of these chemical quantities as conversions between units that we're interested in. Why do we have to use these? Well, because in the real world, we can't measure the number of moles directly, and we can't measure the number of things directly. And we can't measure the molar ratios directly, right? Those come from the chemical formulas of the molecules. So usually we measure something like mass, and then from everything else, we get these relationships. All right, any questions on that? Because that's kind of the basic, theory of what we talked about last time. Summer?
With Avogadro's number,
Mm-hmm.
we're always going to use that 6 point that and then the number of things. And so like we'll multiply that Avogadro's number to the number of things.
You multiply the Avogadro's number to the number of moles if you want to get the number of things, right? If you want to get the number of moles from the number of things, then you do the inverse of that, right? And so we've done some practice examples of that. We'll have more to deal with that as well. And remember a good thing for the exam to have on your note card would be, and something to practice while you're doing the problem sets and labs and everything, is something like this right here, right? Where this is our flow chart of all the different things that we can go between. All right, if you can identify what the problem gives you, let's say the problem gives you the number of molecules of a specific compound, and it wants you to find the grams of a specific atom within that molecule, right? So it's given you this, given, and it wants you to find this, right? So identifying what you're trying to solve for is very important in these problems, and what's given to you. You can see that will give you then a pathway to get to that point, right? That's one pathway. There's also another pathway you can do. And a lot of these problems will have multiple ways you can solve them. And if you're just keeping track of what should be in the numerator, that would be the elements that are in the box here. And these are your conversion factors that you use to go between. I know there's a lot of things that I just circled right here, so it looks a little messy. But being comfortable with being able to use this chart, at least to go from one spot to the next, will be very useful, right? Eventually you'll just know, like when I do it, I can just write the unit conversions there, but you'll be able to build a flow chart like that just in your head. But this is kind of how we build the initial flow chart for our unit conversions, right? And we're just starting off. Okay. All right, so let's start off with an example. How many grams of oxygen are in 32.5 grams of H2O, of water, right? So you're given a mass, right? So we're given a mass here of H2O, 25.2 grams, and you want to find the grams of the element. So see if you can use that to then develop your flow chart as to how you will get there. I'll go back to the problem. Their flow chart done at least. All right, so we're starting from grams of H2O. What's the first step here? Yep, we go to moles of H2O. Right, and the reason we go to moles is because moles allows us to convert between different elements or molecules, either in a chemical reaction or within a chemical formula, right? Moles gives us the actual ratios of those amounts. And how do you convert between those two? Like what quantity do you use? Yep, you use the molar mass. And you use the molar mass of H2O, right? Because you're trying to find the moles of H2O. After you get the moles of H2O, what's the next step? Where are you trying to convert to? Moles of what? Of oxygen, right? Because we have moles of H2O, right? And then we want to go to moles of oxygen afterwards. So we go to moles of oxygen afterwards. And we can convert between those two because we know how many moles of one thing is related to the moles of the other, right? And what allows us to relate those two things? The molar ratio, right? And the molar ratio we get from what? The chemical formula, right? It's related to the subscripts. So for every 1 molecule of water we have, how many atoms of oxygen do we have? 1 to 1, right? Which means if we have 1 mole of water, we get 1 mole of oxygen in those cases. And then after we have the moles of oxygen, what's the final step? Convert to what? Grams of oxygen. And how do you get the grams of oxygen? What do you use there? The molar mass of what? The molar mass of oxygen, right? So that's the distinction here is that when we go between moles of oxygen and grams of oxygen, we have to use the molar mass of oxygen, not the molar mass of water, right? This first step, we use the molar mass of water because we're going between grams of water and moles of water. All right, so those are all our conversions that we're going to be using here, right? Once we have this, then we can start plugging in numbers and messing with the conversion factors to then make sure we're at the right step along the way. So we start with 32.5 grams of H2O. This is what we're starting with. And how do we use the molar mass to get to moles of water? What do we do with it? So if we multiplied it, right, it would be, what is the molar mass of water? 18.00 grams of H2O per 1 mole of H2O. Right? So if we multiply it, we see that the grams aren't going to cancel out. Right? So we have to divide by the molar mass. Right? I'll plug that in just so we can see. 0.00 grams H2O for every 1 mole of H2O. We see the unit that we want is in the denominator, which already tells us that's one way of realizing we're not on the right track. Or the units of grams can't cancel out because they're both in the numerator of this calculation, right? So these will not cancel out, which means that we have to flip this. So we have 1 mole, 1 mole H2O for every 18.00 grams of H2O. Now we see that we're in moles of H2O, which is what we have in the numerator here, and the grams cancel out. Right, so our first step is fine. Sam?
Why is it 18 and not 18.02 grams?
You can put 0.2, that's fine.
Okay.
It just depends on the periodic table you use. Some are more accurate than others. I'll put 18.2 to be thorough there. For these problems, if you're off by a decimal place, usually I'm not going to give you any points taken off, just because, some of you will look at your periodic table for your exam. The other you might look up there. That one has 4 decimal places, and I think the one on you guys has only 2 decimal places, right? So it just depends on how accurate the periodic table is. The thought process is more important for these ones. All right, and then next thing is to get to moles of oxygen. We use the molar ratio. And so how are we going to use the molar ratio? What goes in the numerator and what goes in the denominator?
1 and
Yep, we have 1 mole oxygen because that's where we want to end after this next step per 1 mole H2O, right? We know we want moles of H2O to cancel out, right? We don't want those units left in there at all. So now moles of H2O cancels out. We're left with 1 mole of oxygen, which is what we want for this step in our conversion here. If we were going in the opposite direction, then we would flip the molar ratio. Right, so we're keeping track of our units at each step along the way here. And now we're in moles of oxygen. Our final step is to get into grams of oxygen. So what do we use for that?
Grams per mole.
We use the molar mass, right? And the molar mass of oxygen is what?
16.99.
We'll do 15.99 because why not? Grams of oxygen per 1 mole of oxygen. We multiply it because we see that the moles of oxygen now cancel out and we're left with units of grams, right? And that's what our final answer needs to be in, right? So moles of oxygen cancels out and we're left in grams of oxygen, which is what we want for our last step. And if I had to guess, I'd say you'd probably get close to 35 grams. Probably wouldn't be that far off.
You said 35.
It probably, if I'm just estimating the number without plugging into my calculator. It's like, well, how do you know that? Well, I see for each water molecule, almost all of the mass is in that single oxygen atom, right? Each hydrogen only has a mass of 1 gram per mole. So it's really only about, 1 part in 18, or 2 parts in 18, so 1/9 of the mass is from hydrogen. The rest is from oxygen. You might get something like 29 or something as well. What did you guys get for the grams of oxygen after plugging this all in? 28 point what? 0.8 grams of oxygen. In these calculations, the only thing that's going to determine the sig figs would be the original mass that's given to you here, right? The molar masses that you're given, those are dependent on the periodic table, right? So those don't count towards sig figs. It's only the mass that's given to you. All right, how do we feel about that? Thumbs up, thumbs to the side, thumbs down. All right, so we have one more that we'll look at. And for this one, we're not going to go through and solve the final number. I just want you to find the flowchart for going through this question. All right, so what is the flowchart for this problem? So where are we starting from? What units are we starting from?
52 grams of
Yep, grams of benzene. Right, that's the organic molecule that we're using. And what's the conversion going to be, the first conversion going to be to? Moles of benzene, right? C6H6. And what do we use to convert between those two? The molar mass of what? C6H6, right? Benzene. And how are we going to use that molar mass? Are we going to multiply or divide by it? We'll divide, right? Because we want to end with units, so we divide by the molar mass of C6H6 because we want to end with units of moles of benzene. And once we have the moles of benzene, what's the next step?
the molar ratio.
Yep, we use the molar ratio. And that converts our moles of benzene into what? Moles of hydrogen, right? Moles of hydrogen. How do you know you need to go to hydrogen? Well, we know eventually we need grams of hydrogen, right? We know eventually we need grams of hydrogen. So we first have to get to moles of hydrogen before we can get to grams. And what is the molar ratio? Which version of the molar ratio would you use? So we'd have moles of hydrogen over moles of benzene. And what's the ratio here? How many moles of hydrogen per mole of benzene?
1 to 6.
Yep, 6 moles of hydrogen for every 1 mole of benzene, right? We know we're going to use this form because it has moles of hydrogen in the top, and that's the unit we want for the next step. After we get moles of hydrogen, then we use, what's the last step? What are we trying to get to? Grams of hydrogen. All right, and how do we do that? What do we use? The molar mass of what? Hydrogen. And how do we use it? We're going to multiply it because we want the units of grams in the numerator, right? So we use the molar mass of hydrogen. Right, so this, once you've developed this, this is 80% of the work for the problem, right? The rest is just plugging in numbers for this. So if it's on a quiz or an exam, and you're like, I'm stuck for the problem, if you can at least write this without plugging in the numbers, I'll give you them, a lot of the credit for that problem. Because this is, the actual chemistry of what's going on. Everything after that is just math. It also means that when you're doing these problems, it's important to make sure you write your units, right? So units are very, very important for whatever answer you give. You need to be careful when you're dealing with your units. All right. Any questions on getting this flow chart for the progressive work for this? No? All right. So that's all we're going to do for this one. You can go through and solve for it on your own if you want, or come to office hours and we can go through the math of it. We're going to move on now to using stoichiometry for chemical reactions to do similar types of calculations. Right, that was from office hours. Right, so this is the quantitative relationship between the products and reactants in a balanced chemical equation, right? So what does a balanced chemical equation mean? Without looking at the second one.
I think each side is
There's something that's similar about each side, right? What's similar about each side for a balanced chemical equation? The charge has to be similar, so that's one thing for a balanced chemical equation. Sam?
Same atoms.
Yeah, we have the same number of atoms on each side, right? So that's what we spent last week when we went over chemical equations. Balancing them is important. That tells us that mass is conserved. We have the same number of atoms on one side to the other side. Why? Because we're not going through any nuclear fusion or fission processes, so atoms remain the same. We're just breaking bonds and reforming bonds in a chemical process. All right, so this balanced equation this means we have the same number of atoms on each side. And we're going to develop a kind of similar molar ratio, and we'll still call it the molar ratio, how we do between elements in a molecule and the molecule itself, except now we're going to be using chemical equations to do the same thing. We're going to be thinking as the total chemical equation, that's going to be like the molecule, and the individual elements are like the molecules that are undergoing the chemical change. You say, well, what does that mean? Well, we'll talk about that in a second. Okay. So here we have a chemical equation. We have nitrogen gas reacting with hydrogen gas to form ammonia gas. And so we can check to see if it's balanced. There's 2 elements on each side of this reaction. What are the 2 elements? Nitrogen and hydrogen. So we'll write it for our reactant and product side. On the reactant side, how many nitrogen atoms are there? 2. And how many hydrogens? 6, right? Because there's 3 H2 molecules, means there's 6 total hydrogen atoms. And what about on the right-hand side of this equation? How many nitrogens do we have? We have 2, right? Because what's the subscript for nitrogen? 1, right? And we have 2 of those molecules, which means there's 1 nitrogen per molecule, 2 total nitrogen there. All right, so we're still keeping track of subscripts even in balanced chemical equations. In fact, they're very important. When we're balancing them, we can't change the subscript though, right? We can only change the coefficient, the number that goes in front of the molecule. And how many hydrogens are there now? 6, because the subscript for hydrogen is 3, right? Subscript for hydrogen is 3, and we have 2 total molecules, right? So just to review, this number represents how many molecules of this we have. The subscripts tell us how many of that atom are in that molecule, right? So here we have 3 hydrogen molecules, and each hydrogen molecule has 2 hydrogens. We just have to count up the total number of hydrogen on each side of the reaction to check if it's balanced. So is this equation balanced? Yeah, it's balanced because we have the same number of everything on both sides of this reaction, right? This was our reactant side, and this was our product side. And so, if we have one reaction happening, what the chemical equation is saying is that for one reaction to happen, we need 1 nitrogen gas molecule, we need 3 hydrogen molecules to then form 2 ammonia molecules, right? So we need that number of molecules to make that number of ammonia molecules, right? We need these exact amounts for one chemical reaction to happen. You say, well, why? How does that make sense? Well, I'm sure it's a very complicated chemical process if you were to look at the atoms in undergoing this change, right? It's probably very violent, and there's a bunch of molecules that have to come together in a very special way for this reaction to even proceed. But we know from stoichiometry that that's how many molecules of each reactant we need to form that many molecules of product. And so for the reaction to happen once, we need 1 nitrogen molecule, 3 hydrogen gas molecules, and to form 2 ammonia molecules. If this reaction happens 100 times, now we need 100 nitrogen gas molecules with 300 hydrogen gas molecules to form how many ammonia molecules? 200, right? We need this combination for this reaction to happen 100 times. For 1,000,000 times, how many nitrogen gas molecules do we need? Yeah, we need 10 to the 6, right? Nitrogen gas molecules, right? We need 1,000,000 of them. And how many hydrogen gas molecules do we need? 3 million, right? All we're doing is 1,000,000 is our counting device. 1,000,000 is like our mole, right? We know 1,000,000 means 10 to the 6, whatever it is that we're talking about. So we need 3 times 10 to the 6 hydrogen gas molecules. And then how many ammonia molecules are we going to make? 2 million, right? 2 times 10 to the 6 ammonia molecules. Right? So now we're just adding, okay, this reaction to happen more times. We just multiply whatever that coefficient is by the number of times that reaction is happening, right? So if this reaction happens a mole times, how many times is that reaction happening? .022 times 10 to the 23 times, right? But it's easier to write how many times? 1 mole times, right? That's a lot easier to write 6.022 times 10 to the 23 times. So how many moles of nitrogen do we need then for this reaction to happen 1 mole times? 1, right? We just need 1 mole of nitrogen molecules for this reaction to happen 1 mole times. Why? Because the coefficient up there is just 1. What about hydrogen gas molecules? How many moles of hydrogen gas do we need? 3 moles of hydrogen gas molecules. And what about ammonia molecules? We make 2 moles of ammonia molecules. right? So the same way we deal with atoms, right? It's easier to deal with moles of atoms and molecules because they're so small. Because they're so small, it means when you mix, 1 cup of water with another thing that it's going to react with, the reactions that are happening a bunch of times, right? How many times? They're happening a mole times. So we can use these coefficients, our stoichiometric coefficients in the chemical reaction, to make our molar ratios the same way that we did for molecular formulas and for atoms within those molecules. All right, so these are going to be dealt with exactly the same way. So if we were to make molar ratios for this, for every 1 mole of H2 molecules, how many moles of ammonia molecules, NH3, is that going to make?
Can you answer the question again?
For if we have 1 mole of hydrogen molecules, or sorry, not hydrogen molecules, I meant to put nitrogen there, it's under the wrong. For every 1 mole of hydrogen molecules, how many moles of ammonia does that make? 2, right? Because we need, if we have 1 mole of nitrogen molecules, we make 2 moles of ammonia, right? So that equals 2 moles of ammonia.
Even without considering the hydrogen?
Even without, because we're not even worried about the hydrogen right now. And so when we deal with these problems, a lot of times what they'll say, unless you're determining a very specific thing we'll talk about on Monday, is we'll say, okay, there's just excess hydrogen. We don't have to worry about how much hydrogen because we only have 1 mole of this. That's the important thing. But we can also phrase the question, if we want 1 mole of nitrogen gas to react, how many moles of hydrogen do we need for all of the nitrogen to react? We need 3 moles, right? So that would give us a ratio then between 2 of the reactants within the reaction. So 1 mole of nitrogen also equals 3 moles of hydrogen. So for each of the stoichiometric coefficients, you get a relationship in this case because there's 2 reactants in 1 product. You get a relationship between the element that you're going from to the other reactant or to the product in this case. And then from each of these equalities, you get what? From each of these conversion equalities, you get 2 conversion factors, right? You get 2 ratios that allow you to go between the moles of these substances. Right, so the way these questions are going to be phrased is, let's say I have 2 grams of nitrogen gas. How many moles of hydrogen do I need to react all of the nitrogen? So you convert the nitrogen of grams of nitrogen to moles, the moles of nitrogen to the moles of hydrogen, and then the moles of hydrogen now to the moles, or the grams of hydrogen. Right, so it's going to be the exact same thing, except instead of using the chemical formulas, we're using the coefficients in the chemical reaction to do these calculations. Right, so we'll do this quick example here, and then we'll take a little 5-minute break because I know we've done a lot of calculations today. So determine the mole ratio of each, determine each mole ratio based on the reaction shown. Right, so and we'll just do this for one example. Do this for oxygen to all the other quantities, or all the other species in this chemical reaction. Okay, so we'll do one together and I'll let you guys do the other 3. So if we're going from oxygen to, this is going to be butane, C4H10, what's the molar ratio going to be for that? we're going to butane C4H10. So moles of butane should be in the numerator or the denominator? In the numerator, right? And how many moles of butane do we need per moles of oxygen here? What are the numbers going to be for this, right? So we're going to have C4, we're going to have mole C4H10 over moles of O2. And what are the numbers going to be here? Yep, we have 2 moles per 13 moles of oxygen. Where do we get that from? This 2 comes from the coefficient here, and the 13 comes from the coefficient there. How would I say this in a sophisticated way? Well, if I have 13 moles of oxygen gas, I need at least 2 moles of butane to react all of the oxygen gas here. All right, so see if you can do the other 2, which will be O2 to H2O and O2 to CO2. So what's the ratio going from oxygen to water?
That'd be 10 moles of H2O,
10 moles of H2O per,
8 moles of O2.
shouldn't be 8, because how many moles of O2 do we need for the reaction to happen 1 mole times? We need 13, right? This is CO2, right? And this is oxygen. We can't change the chemical formulas on either side of the reaction. So we're going from O2, not CO2. So that's why it's not 8 in this case. So we have 13 moles of O2. What about from oxygen to CO2? 8 moles of CO2 per 13 moles of O2. Right? And the only reason we have the ratio in this order is because I'm saying we're going from oxygen to CO2. If we're going the other way, then these ratios would be flipped. All right, any questions on that? Because I know this is not easy. Vanessa?
So essentially, like, the easiest way to look at it is just looking at the coefficients and
Yeah.
that just tells you the ratio.
That's exactly right. The coefficients, the same way the subscripts tell you the ratio for the problems we did before, the coefficients here are going to tell you the ratios for the chemical reaction. And so in these problems, because I'm explicitly asking for you, it makes a little bit more sense. But if I say, and what we'll look at is if I have, okay, there's 13 grams of oxygen, how many moles of water do you make? That's where it becomes a little less clear. But you have to know, because I'm giving you a chemical reaction, the molar ratio I'm using there is from the chemical equation. But yeah, it's in a simplified way, that's the easy way to look at it. The coefficients give you the molar ratios. All right, let's take like a 6-minute break. We're back at 2:40. All right, so this is how we get our molar ratios from chemical equations now. This is the only thing that's changed in the problems from before, right? So we still use the molar mass the same way to go from mass to moles of a compound. The only difference is now the molar ratio, when we go from moles to moles, comes from the chemical equation. And so you can think of it, generally when we're going from a reactant to another reactant, or a reactant to a product, or a product to another product, we have to convert everything into the universe of the moles to go between them, right? So right now we're usually just dealing with mass because those are the only tools we have is looking at mass. But in the future we might look at pressures of gases, concentrations of solutions and things, to then also do these types of calculations. But the same idea, the idea is still the same. Once we get the number of moles, we can convert from one side of the equation to another side of the equation, or from a reactant to another reactant, and so on. Okay, so what are these types of conversions we do? Usually, we do one of these 4 things right now, right? Because we don't know what concentrations are, and we don't know what pressures are. So we can only go from the mass of one compound to the mass of another, or any variation of this, right? If we just wanted to find the moles of compound B from the mass of compound A, that would be our pathway. If we want to find the mass of compound B from the moles compound A, that would be our pathway. In these compounds, these are compounds that are involved in a chemical reaction, right? So these are involved compounds involved in a chemical reaction. And we need to convert whatever amount of compound we have into moles first before we can go between compounds. Right? So again, we go into the universe of the moles, and that's what allows us to go between compounds. So if we have the moles of one compound, and we want to go to the moles of another compound, we just use the molar ratio, right? So this is just this was just the bottom part of the previous flow chart, right? All we need for this is a balanced chemical equation. So a relatively layered problem for doing these calculations would be giving you an unbalanced chemical equation, you balance it, then you do these conversions afterwards. Right, so again, once we're in moles, then we can go between compounds here. Vanessa?
So you can use the molar ratio to go between, I mean, like obviously the moles of compound A and compound B, but we could also do it to like the mass or no?
We can also do it with the mass, because if we, have the molar mass of whatever, and as long as we have the chemical formulas, we'll have the molar mass of those. Then we can go between the mass of compound A and the mass of compound B, or vice versa. You just have to convert them into moles first before you can go between them. Right, so going between masses is 1, 2, 3 steps, whereas going just between the moles is 1 step. Right, so that just means you have more steps to do in your calculation. Okay, so here we have the same equation chemical equation we had before. And this is a way these type of questions will usually be asked. So they're asked usually in a chemical context, right? Not just what is the mass of this given this much. They'll say how many moles of nitrogen will react with 2.4 moles of hydrogen to produce ammonia as shown in the reaction below. Right? So what this question is saying is how many moles of nitrogen will react with 2.4 moles of hydrogen. Right? This means that another way of phrasing this is how many moles of nitrogen do we need to react 2.4 moles of hydrogen? Right, so in other words, how many moles of nitrogen are needed to react all 2.4 moles of H2. Right, so we have to decipher a little bit what the question is asking us here. So we're being asked to solve for what?
The moles of nitrogen.
Yeah, we're being asked to solve for moles of nitrogen, and we're being given what? We're given the moles, 2.4 moles of H2. So how are we going to go from moles of H2 to moles of nitrogen? Yeah, we use the molar ratio, right? Because that tells us it converts moles of one compound to moles of another. Right? These are both on the reactant side, which is why the question is phrased this way. How much nitrogen do we need to react all of this hydrogen we have? Like, what is the bare minimum amount of nitrogen we need to react all of this? And so we start with, so we use the molar ratio, 2.4 mole of H2. Then we use the molar ratio. And what is the molar ratio between nitrogen and hydrogen here? What goes in the numerator and what goes in the denominator? Yep, hydrogen goes in the denominator because we want nitrogen in the numerator, because that's the unit we want to end with, right? So we have mole nitrogen, mole hydrogen. And what are the numbers associated with these? It should be 1/3. Where do we get those numbers? The balanced chemical equation, right? These come from the balanced chemical equation. So what happens to our units of moles of hydrogen? They cancel out, and now we're in units of moles of nitrogen. Okay, and so we plug that in, 2.4 divided by 3 should be 0.8 moles of N2. And what we would say in words is that we need at least 0.8 moles of N2 to react 2.4 moles of hydrogen here. All right, so this is just a one-step conversion. Why? Because we're already in units of moles. Once we're in units of moles, we can go from one compound to the next. As soon as we introduce mass, well, mass isn't directly related to any other compound. We have to convert it to moles first before we can go between compounds. All right, so any questions on this conversion here? This would be 8.0 just because there's 2 sig figs, so I'll just make sure. Summer?
So if we had to, do another step,
Mm-hmm.
it would be because instead of that being mole, it would be something like atom, like,
You could go to atoms, right? We could make it complicated going to atoms, right? Because you can go between atoms and moles too. But if I gave you, instead of 2.4 moles of hydrogen, I gave you the grams, right? And that would probably be like, what's 1 gram? How much do we need to react 1 gram? First, you have to use the molar mass to convert it to moles, and then you convert it into moles of nitrogen. And so, if now you had this and I said, well, how many grams of hydrogen is that? How would you do that? Or not hydrogen, nitrogen. How many grams of nitrogen did you use?
so now we would go from moles of nitrogen to moles of nitrogen. No, grams of nitrogen over moles of nitrogen?
Yeah, you would use the molar mass to convert this into grams, right? You know the number of moles, and you know, because we have the periodic table, you know then how many grams this many moles should be equal to. All right, good question. Okay. So here's another way that this can be expressed. How many moles of ammonia can be produced from 32 moles of hydrogen, right? Assume excess nitrogen. So the only thing that's changed here is assume excess nitrogen means that there is enough nitrogen to not worry about it. Right? That just means you have so much nitrogen that it's really the hydrogen that's limiting how much you can make. Right? We'll talk more about limiting reactant and stuff next week. But it's saying we have so much nitrogen that how much ammonia we can make is limited by the amount of hydrogen that we have. Right? We're asking how many moles of ammonia can be produced. Right? So what are we trying to look for here? We want to find moles of ammonia, right? That's what we want to solve for. And what are we given?
Moles of hydrogen.
The moles of hydrogen. We're given 32 moles of hydrogen. So how do we convert between these two?
Moles of hydrogen.
What chemical quantity do we use for a chemical reaction? Yeah, we use the molar ratio, right, Zendaya? We use the molar ratio, which we get from the balanced chemical equation. So we're starting from 32 moles H2, or I'll just put mole H2. You can use both, but I'm trying to be consistent. And what's going to be our ratio? What goes in the denominator and what goes in the numerator? Ammonia should be in the numerator because we're trying to solve for moles of ammonia, right? And in the denominator, we want moles of hydrogen to cancel out. And what are the numbers that are going to go there? What goes in the numerator? 2, right? Because 2 comes from our balanced chemical equation. In the denominator, we have 3, right? Because we have 3 moles of hydrogen for every 1 mole of this reaction that happens. Question, Simon?
Cause I'm looking at, I keep on looking at the subscript,
Mm-hmm.
that 3 and thinking it's 6.
That's important when we're balancing the reaction. Remember, the stoichiometric coefficients, they don't tell us anything about the subscripts of the molecule. It just tells us that we need this many molecules for the reaction to happen, right? So in this case, I can see why it'd be confusing because you're asking about hydrogen. When we say hydrogen, we're always talking about the gas form of hydrogen. That's one of the 7 diatomic elements that are found naturally.
H2 is-
Yeah, so H2 we just call hydrogen. Yeah, that's why if you guys are confused about that, it's a good question. Nitrogen, right? It's like, well, why aren't we doing single atoms of nitrogen? Because in chemical reactions, you won't see a nitrogen atom on its own ever. It'll always be in the form of nitrogen gas or in some other molecule. So we just call nitrogen N2. N2 is just nitrogen, right? We don't call it dinitrogen, for example. And that's just because that and all of the halogens, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen are the elements that do that. That's a good point to bring up. Interestingly enough, for more complicated chemical equations, you won't run into that issue because you won't just have hydrogen there. It'll be molecules that will have specific names. Okay, so what happens to moles of hydrogen here? They cancel out. And then we get 64 divided by 3, 21 moles of ammonia. And so even though we're not given, well, in this case we are, but in the previous problem we're given a whole number of moles that we're starting out with, the coefficients give us whole number ratios for the chemical reaction to proceed. So that's how we can convert numbers that aren't necessarily whole, like the previous problem, to the moles of interest. All right, any questions on that? Or any more questions on that? All right, so there's one more example, but we'll go on to the next type of conversion, right? So these are going to be broken down into, just moles to moles, mass to moles, and then mass to mass, right? So if we're given the mass of a compound, and we want to convert to moles of another compound, the only thing that changes now is that we have 2 steps, right? First, we have to convert mass to moles, and then second, we convert moles to moles, right? So it's the exact same thing we did previously. We just have one more step in there because we have to get to the universe of the moles to go between compounds in these cases. Okay, just waiting for people to finish, right? Okay. So using the same chemical equation, how many grams of ammonia can be produced from the reaction of 1.8 moles of nitrogen? Right? So what are we being asked to solve for here?
Grams of ammonia.
We want grams of ammonia, right? And what are we given?
Moles of nitrogen.
Moles of N2. We're given the moles of one compound. We want to solve for the gram. So what's our flow chart going to be? We're starting from moles of N2. What do we convert that to? So here, a couple different answers, right? I hear some people saying grams. Why can't we go to grams right away? Because we can only go from moles either to grams of this compound, right? But that doesn't help us necessarily, right? Because once we get to grams of this compound, that's not related to the grams of ammonia in this case, right? We're already in moles, and we want to find grams of what? Ammonia, right? So first, before we get to grams of ammonia, we need to find what? Moles of ammonia, right? And we're already in moles. So we go from moles of ammonia to then grams of ammonia. This question also could have been asked, if we have 2.3 grams of nitrogen, how many moles of ammonia would we get? And then we'd have to do the molar mass calculation first. So how do we go from moles of nitrogen to moles of ammonia? What do we use? The molar ratio. And what about from moles of ammonia to grams of ammonia? Then you use the molar mass, and the molar mass of what? Of ammonia, right? Right, because once we're in moles of ammonia, we can only go to grams of ammonia using the molar mass. So if we start with 1.8 mole N2, what's the molar ratio between N2 and ammonia? What goes in the numerator? 2 moles ammonia per how many moles of nitrogen? 1 mole nitrogen. All right, we see that that gives us moles of NH3, which is what we want, and moles of N2 cancel out. And then the last step, we use the molar mass. And how do we use the molar mass? Do we multiply or divide it? All right, what is the molar mass of, let's do the, just to review, right? What is the molar mass of ammonia equal to? 17.03, and that's equal to 14 point what? What is nitrogen? I can't see. That's okay, we'll just do 14.00 grams per mole. And again, these are in units of grams per mole, plus 3 times 1.008 grams per mole for each hydrogen atom, right? This is the molar mass of hydrogen, and this is the molar mass of a single nitrogen atom, right? Again, to get the molar mass of any molecule, you add up the molar masses of all the elements that you see on the periodic table. So that gives us 17.03 grams per mole. So what goes in the numerator here? 17.03 grams ammonia per 1 mole ammonia. right? Because that's our molar mass. We want the moles to cancel out and end in units of grams. That's what we're trying to go to. So moles of ammonia cancels out, and we're left with grams of ammonia, which is what we want to solve for. And so when we plug that all in, get 1.8 times 2 times 17.03, I get 61 grams of NH3.
Wait, why is it only one more NH3?
Because this is the molar mass, right? And the molar mass is given in units of grams per mole,
Okay.
which is whenever we have the fractional units, it's like dividing the whole thing by one of that unit. And I know that sounded complicated, it just means it's 70.03 grams per mole, which just means that's the exact same thing as writing 17.03 grams of ammonia per 1 mole of ammonia. Because 17.03 divided by 1 is just that number. All right, so we'll end there. We'll start lab at 3:25 today.